right. Welcome, everyone. Neuro-Symbolic Wednesdays. Are you seeing my slides? Okay, great. So we're going to give it a few minutes, per usual, for people to roll in. Today, is it? Help me with the pronunciation so I don't screw it up.
Suguman Bansal.
Okay, good. That's what I thought. By the way, fond memories of Georgia Tech, so it was nice to see that.
I have to ask how to start deliberately.
Yes.
Hi, Olga. Hi, Alex.
Hi, Suguman. Thank you for joining us today.
Thank you for the invitation. We are thrilled to share our work.
Alex, when you start, would you please enter the presentation mode?
Yes. I'll do that
I
now.
am in presentation mode. Am I in presentation mode? Can you check?
No, Suguman, for you, it will your screen will be switched later. It's currently, I believe it's Alex's screen for now.
Yeah. We'll start with, I'll just show a few slides as an introduction. While we're waiting, I don't want people to miss my intro of Suguman, but while we're waiting for folks who maybe are new to this, these are the various ways you can join. Main place is Discord to end up at, but you can watch from YouTube. You can check out software on GitHub. Connect with us on LinkedIn. Our learning site we talked about recently, what that looks like. You can check it out. It's we're about to do a big put a big amount of stuff there, so look for that. There are other ways to participate you can see on the Centaur website. Oops, I'll come back to that, but we're gearing up for this, as we've mentioned a few times. So those interested in this kind of a thing, especially programming languages people, systems people, let us know. And looking for people who want to present something. It doesn't have to just be these papers. Could be a few other classic papers you could propose. But we are looking for people who might want to present any of these.
Alex, maybe not only classic papers. If someone has recent research somehow related to Neuro-Symbolic AI, do you think we can consider these as well?
Oh, yeah, absolutely. If you want to volunteer, you have a paper. Of course, we'll just send us an email. No guarantee, but we'll consider anybody who wants to present. All right, I'll just leave this up so you can know what these are. Also, different research threads that we have ongoing, including all the way at the theory end and all the way at the system building end. All right, plus some of the usual neurosymbolic topics. And as far as funding, the real way to get funding with us is just start hanging out with us. That's the mark of, alignment on interests. Is you just start doing stuff with us.
Alex, do you think we can mention summer schools?
Oh yeah, good. So the summer school, we should have made a slide on that, but coming up. So you have thoughts on it for us? It's August 6th and 7th. As call it tentative date, but I think it's pretty much fixed now. So mark that on your calendars. Anything else we should say about the summer school, Olga, you think?
Unless, Alex, you have some big names to announce already. Maybe nothing else at the moment.
There will be big names. Okay, maybe that's enough time. Now let's get started. So today we're honored to have Suguman, assistant professor at Georgia Tech, and part of the very important thread in Neuro-Symbolic AI, which is bringing in formal methods. So this, I think, is, well, we'll hear. I don't want to take the thunder away, but extremely important in my view. And I want to announce in 2 weeks, Yashi, some of you know, speaking, and there may be a talk next week, or we'll see. All right, and with that, let me hand it over to Suguman.
Thank you, Alex. Thank you for the introduction, and it was great to learn about all the ways that TOR engages with Neuro-Symbolic AI, which is sort of the very broad area all of us work in. So I will talk about specification-guided reinforcement learning, and the neuro-symbolic bit here is the symbolic bit is specification, and neuro bit is reinforcement learning. And this is work that I have been pursuing for the past few years with collaborators, mentors, and students. So while we're still getting comfortable in our seats, the very broad question that I'm chasing is how do we develop trustworthy AI? And the direction I am looking at is can we do it through integration of formal methods with artificial intelligence? Now, AI is ubiquitous. It is shaping our present and future. AI is really, really ubiquitous. It is in our smartphones, in medical diagnostics, transportation, e-commerce, smart homes, social media. It's very true that AI is no longer the future. It is the present we live in. And AI today is very, very good. So good that when I asked ChatGPT to prepare a slide on the ubiquity of AI, it gave me a very clean description of what the slide should be, all the way up to the tagline that AI is no longer the future, it is the present we live in. But fun and games aside, as ubiquitous as AI is, it is not as trustworthy. If we look at safety critical domains, law, medicine, transportation, and so on, it is difficult to put trust in the current AI algorithms. And as this article very nicely puts it, the issue with AI approaches is that the algorithms don't explain their decisions. And when there is this complete lack of transparency, there is this complete lack of understanding of how these algorithms work, it is very difficult to trust AI for safety critical domains. And the way I'm looking at, there are multiple ways of addressing this question. The way I have been thinking of it is in terms of using formal methods in AI. Formal methods is a very well-established field in computer science where the very broad objective is to design systems that are safe, reliable, and trustworthy, and to make the design of such systems as simple as it can be. While formal methods may have begun as a purely logic-driven and mathematical domain, today through collaborations with industry and academia, formal methods does find critical applications in hardware systems. All hardware chips that are shipped for actual public use have been formally verified. This is a critical pipeline in all hardware development today. The other recently formal methods is finding more and more application in software development where several tech giants do deploy a formal verification, formal methods pipeline to ensure that the software is correct with respect to certain parameters. And the vision here is that the next generation of formal methods research is in developing trustworthy AI. There are various AI domains, and today AI systems are able to solve very, very difficult problems. But in most cases, these problems are not verifiable. It is hard to trust the output. And the question is, can we use formal methods to increase the trust in any of these AI systems that we see in deployment today, especially in safety critical systems? So the focus of my work is I envision to address this trustworthy AI problem using the three pillars of formal methods. And these three pillars are task specification, verification, and synthesis. Task specification says, how can we precisely express the intent? We want to design a system. What is the purpose of the system? And can we formally specify the purpose or the intent of the system? Verification says, given a system and given its intent, can we verify, can we ensure that the system satisfies the given specification? Synthesis takes the dual approach here. Oftentimes, it is easier to write a specification than designing a system from scratch. And taking this view, synthesis says, how can we build a system from a given specification? So if I can specify my intent, can I automatically build a system that is correct by construction? Now, this talk focuses on the synthesis question. And here is very broadly what the synthesis problem is. In formal methods, we are given a model of the environment, and we are given the specification in which we're given a specification. The objective is to build a system. Now, what synthesis algorithms will do is that given a model of the environment and given a specification, it will build a system that is correct by construction with respect to the specification. So if I want to build a controller for a specific task in a robot, I would input what the environment is, the environment in which the robot will operate. I will say what the specification is. Perhaps it is to destack a tower of blocks. And then the output would be a controller which is verified to fulfill the task of destacking the blocks in the environment. The issue with AI systems, now this is how formal verification works, formal synthesis works. The issue is that, or the core aspect of why formal methods is able to give guarantees is because we assume that the environment is given to us and the specification is given to us. So we have a good model of both the environment and the specification. And then we can ensure, and then synthesis algorithms can ensure that the system is correct to the given specification. The challenge with AI systems is that oftentimes the environment is too large or uncertain or maybe unknown, which means that we cannot model the environment precisely. Similarly, the specification may be imprecise, it may be noisy, or in many cases might even be unavailable. Again, when we're talking about the synthesis of AI systems in particular, then the specification is also not precise and not given. So given these imprecisions and uncertainties in both the environment and specification, the challenge becomes, can we really design AI systems that give guarantees of correctness? If this environment and specification were known, synthesis algorithms can guarantee correctness, but in the absence of knowing the environment and the specification, the question is, how do we obtain guarantees from AI systems? So the focus of today's talk is really going to be the synthesis of AI systems, and the synthesis algorithm I will talk about is going to be reinforcement learning. The contents of this talk are based on a recent CSCM article that was published actually just this month with my collaborators, Rajiv Alur, Ospert Vastani, and Kishore Jyoti Murugan. So in this talk, you're really hearing the contents of this article from the horse's mouth. So with that said, and with that setup, let's dive into specification-guided reinforcement learning. So you may have heard of reinforcement learning. This is the third pillar of machine learning. There is supervised learning, there is unsupervised learning, and then there is reinforcement learning. If you really think about it, reinforcement learning is a synthesis problem because the problem of reinforcement learning is, given a task, generate a policy that satisfies the task. So this really is a synthesis algorithm. If you think about it from the formal methods lens, reinforcement learning is a synthesis algorithm. It finds various applications, many applications in controller synthesis for robotics, autonomous vehicles, applications in finance, healthcare, software bug finding, and whatnot. So it's a very, very powerful paradigm, but it is a synthesis algorithm. The key aspect of reinforcement learning is that it assumes that the environment in which the policy will operate in is unknown. So remember, this is an AI system. We do not know the environment. So the environment in which this policy, the output, the system that we want to produce is unknown. In the absence of knowing the environment, the way reinforcement learning learns a policy is it starts with an arbitrary policy. It takes an action in the environment, so it samples the environment. And based on that sample, the environment returns a feedback. Depending on what the feedback is, the policy improves itself, and this cycle continues until the policy can't be improved any further. So if you think about it, reinforcement learning is a synthesis algorithm that operates in a policy improvement loop by sampling the environment because the environment is unknown. Now, traditionally in reinforcement learning, or the way machine learning people think of reinforcement learning, the task that we are designing a policy for is expressed in the form of a reward. For example, suppose I take this really simple task. So now the challenge is that rewards are often, it's very hard to express complex tasks in the form of rewards. And I'll illustrate this through a really simple example. Consider this task. Suppose my task is to go from the initial point to the region shown by P. So my specification is to reach a given area called P. If I were to design a reward function for this really simple task, it would be really simple. It would simply say assign a positive reward when one reaches P, and otherwise assign a reward of 0. Now suppose I make this task a little bit more complex, and I say now my task is to first reach P and then reach Q. Now note that I can't simply take the reward function for reach P and reach Q and concatenate them one after the other. Because if I do that, then I will not be able to, then I may end up learning, then the reward function may end up learning a policy that reaches Q without ever visiting P. And that is not the specification we wanted. So this example is fairly simple, but if you give it a little bit of thought, of course, a direct concatenation of reach P then reach Q will not work. But if you give it a little bit thought, then you can design a reward function that will able to accomplish this task properly. So the reward function will be able to express that you must reach P before you reach Q. Now, the point of this example is that is to illustrate that as the task becomes more and more complex, writing a reward function can become very cumbersome. So even just for reach P then reach Q, a simple concatenation does not work. One has to reward engineer a bit more. As the task will become more and more complex, this challenge of expressing the task in the form of rewards will become more and more complex. So the view that formal methods has taken is that in formal methods, task specification is a very well-defined problem. And in fact, we have many logical formulations that can express such tasks. One such logical formulation is of temporal logics. Temporal logics are used to describe properties over executions. At a very high level, temporal logics consist of logical constraints as well as temporal constraints. So you can say things such as always do something, or eventually reach a certain goal, or do this and then in the next step do this, and so on and so forth. Over the past many years, many temporal logics have been defined, all with certain subtleties about what is better for the given domain. But the commonality between all temporal logics is that they have rigorous semantics. Unlike reward functions, where the semantics is not rigorous, temporal logics have rigorous semantics. The other benefit of temporal logics is that their syntax is very close to natural language, which means that expressing tasks using temporal logics can become significantly simpler than it is to use reward functions. For example, if I take the specification, the task of reach P, in temporal logics, it will simply be expressed as eventually P. And if I take the task of reach P, then reach Q, it simply concatenates eventually P with eventually Q, the way one would say it in natural language. So the area that has been burgeoning for the past decade or so is of specification-guided reinforcement learning, which says that can we design reinforcement learning algorithms where the task is specified using a temporal logic as opposed to using a reward function. Here I've shown the list of papers I've shown is simply to demonstrate that there is a lot of work in this area. This list is by no means comprehensive and by no means updated. It's simply to demonstrate that specification-guided reinforcement learning is a key topic of research at the intersection of within Neuro-Symbolic AI. So the question we will ask in today's talk is, can temporal logics build trust in reinforcement learning algorithms? So we've spoken about trust at the task specification level. Traditionally, if you use rewards, then rewards are non-rigorous. Their semantics is non-rigorous. In contrast, temporal specifications have rigorous semantics. So if you express a task in the form of temporal logic, we can be absolutely sure of what intent has been expressed. The other two parameters that one should think about when you're discussing or when one is trying to compare the degree of trust between reinforcement learning with rewards versus reinforcement learning from temporal specifications are the questions of what can we say about theoretical guarantees? How do the guarantees of rewards fare against the guarantees of temporal logics? And the other question you may ask is, ultimately, we want to use these algorithms for practical deployment. How do these algorithms perform in practice? And do these guarantees also trickle into the practical algorithms? So during this talk, we will try to fill in these four boxes. And by the end of it, we will hopefully all have enough information to make a judgment for ourselves of whether we can build trust in reinforcement learning algorithms by using logical temporal specifications. All right, so with that said, let's dive straight into what reinforcement learning is. I've already given you a very high-level picture of what it is. It is this policy iteration loop. Given a task, you want to learn a policy, and the policy is learned by interacting with the environment. Let's try to formalize it a little bit now. The environment in reinforcement learning is expressed in the form of a Markov decision process, an MDP. An MDP consists of states, a set of actions. Both the states and actions can be infinite in number. We are not restricting ourselves to the case where either S or A are finite in number. There is a transition probability function which assigns a probability of transitioning from a state or a given action to another state. So this tells us how the environment evolves. And there is an initial state distribution that tells us what the initial regions in the environment is. So where will the task begin? To demonstrate this through an example, here is a 9 rooms environment. It is a continuous state environment. It is a continuous environment where both the actions and states are infinite in number. Oftentimes, this picture gives people the impression that this is a finite state MDP with 9 states. That is not the case. This is an infinite state environment where states are XY coordinates in the 2D Cartesian plane. Actions are given in the form of theta d, where theta is an angle and d is a displacement. The transition probability says that the chances of reaching a certain state from a given state according to an action is high according to the laws of physics, and with perhaps a low probability the action might fail and it may go to a failure state. And in this image, the region shown by the blue square S0 is the initial state distribution. So if I'm looking at trajectory, if I'm looking at how will a system evolve in this, all of the systems will begin in the region given by S0. Now, a policy in an MDP is effectively, all it says is that given a history of trajectories in the MDP, can you tell me what action to take next? So given a history of trajectory, given a trajectory, what action should I take next while evolving in this MDP? Now, if we were looking at the problem of reinforcement learning from rewards, this is how the problem is defined. Given an MDP that describes the environment, a reward function, and a discount factor, can you generate a policy such that it optimizes the reward function? So technically, this is the expected discounted sum reward. We don't need to get into the details of what this is. For the purpose of this talk, it is sufficient to know that given an MDP and a reward function that captures the intention of the task, can we generate a policy that optimizes the rewards? In other words, can we generate, the aim is to capture the idea that you want to optimize the chances of fulfilling the award. Now, the key aspect in reinforcement learning is that we assume the environment is unknown. And technically, what that means is that we assume the transition probabilities are unknown. So, assuming the transition probabilities are unknown, can we find a policy that optimizes the reward? Now, if the transition probabilities were known, then this problem is actually very well studied. This ends up being the problem of optimization in MDPs. So if you're given an MDP, a reward function, and you want to find the optimal policy with respect to the rewards, then this is the optimization problem of MDPs. And turns out it has been studied for more than 70 years now. The seminal papers by Shapley from the 1950s show that in these cases, there must exist an optimal policy, and the optimal policy has this very nice form of being both memoryless and deterministic. We don't need to get into the details of it, but what this means is that a policy is simply a map from states to actions. So you don't need to look at the history of the trajectory. It's sufficient to look at the current state, and based on that, you can tell deterministically what action to take next. So these are very, very seminal results in optimization theory, and these are very well studied. It's very well known how to solve these problems. In particular, these problems are solved using Bellman equations. We don't need to get into the details of what these equations are. All I want you to note is that the factor of PSAT is crucial here. Remember, PSAT is the transition probabilities. So when the transition properties are known, you can set up these Bellman equations, and there are various algorithms that can solve these Bellman equations in order to extract a memoryless deterministic policy. So if the transition properties are known, the problem of generating the optimal policy is well studied. However, note that this depends on knowing the transition probabilities. If the P was not known, you cannot set up the Bellman equations, and therefore none of the work built within optimization theory applies to the problem of reinforcement learning. So how do we solve the problem of reinforcement learning? So here is what reinforcement learning assumes. It says that, well, in the absence of transition probabilities, the ability that you are given is to simulate the MDP, which means that you have the ability to sample as many trajectories as you wish of any arbitrary length. And then the objective is, by simply sampling the environment, can you learn the optimal policy? So at a very, very high level, the 10,000 feet view of what a reinforcement learning algorithm is, these are all sampling-based algorithms. Given the simulator, you have simulator access to the MDP. So you want to simulate the MDP sufficient number of times so that you have a good estimation of what the transition probabilities are. And as long as you have a good estimation of the transition probabilities, now you can use the Bellman equations and try to obtain an optimal policy. Right? So this is the 10,000 feet view of what a reinforcement learning algorithm is when the specification is given in the form of a reward. So what can we say in terms of theoretical guarantees here? It is well known that these algorithms have asymptotic guarantees of convergence, which means that if you could sample indefinitely, then the algorithms are guaranteed to converge to the optimal policy. And this is a very, very seminal work by Watkins and Diane from the 1990s. This algorithm is also called Q-learning. If there is one thing you should know about reinforcement learning from rewards, it is the Q-learning algorithm. Most developments of reinforcement learning are based on the Q-learning algorithm. And that algorithm gives asymptotic guarantees of convergence. The other kind of guarantee that one obtains from these reward-based specifications is of pack guarantees, which means that if you could sample for a finite number of times only, as opposed to sampling indefinitely, if you could sample for only a finite number of times, can you guarantee that you will learn a near optimal policy with high confidence? So now we are trading off the number of samples with the precision of learning. And we say that if you sample with a finite number, if you sample for a finite number of times, can you learn near optimal with high confidence? And this is called pack learning. So when we're learning from rewards, what we know in terms of theoretical guarantees is that reinforcement learning from rewards gives both asymptotic guarantees of convergence as well as pack guarantees of convergence. The question is, what do we get if we are learning from temporal logic specifications? What can we say about theoretical guarantees? Right? So before we get into theoretical guarantees for reinforcement learning from temporal specifications, let me formally define the problem of RL from temporal specifications. So similar to how RL was defined for rewards, we start with an MDP, which describes the environment. Instead of rewards, now the task is expressed using a temporal logic specification. And now our task is to generate a policy that maximizes the probability of satisfying the specification. Recall that earlier we had rewards, so we were optimizing with respect to rewards. Now we have a temporal specification, so we are optimizing with respect to satisfaction of the temporal specification. And the key assumption is that we do not know what the transition properties are. Reinforcement learning is when the environment is not known. And once again, it's the same thing here. It translates to not knowing what the transition properties are. So to demonstrate this through an example, suppose here is our 9 loops environment, continuous states, continuous actions. You begin in the region S0. Suppose my specification is to eventually reach the region denoted by S1. Then a policy that generates trajectories as the dotted orange line in the illustration. Any policy that is able to generate trajectories like this is an optimal policy. Now, if the transition properties were known, then learning an optimal policy with respect to temporal logic specification is a very, very well-studied area within formal methods. This is the problem of probabilistic model checking. It is very well understood, very well established. There are tools, it has practical applications and whatnot. But once again, because transition probabilities are unknown, we cannot use any of the work that has been developed within probabilistic model checking. Because this is the reinforcement learning problem, we don't know transition probabilities, we must develop new theory and new algorithms to solve this. So now our objective was to understand what theoretical guarantees do we get if we are learning from specifications, right? So let's go over this really simple example. So here I have a 3-state MDP. There is an initial state, there is an unsafe state, and a safe state. From the initial state, upon taking action A, with probability 1, one transitions to the safe state. And from the initial state, upon taking action B, with a very small probability gamma, one moves to the unsafe state. But with high probability, 1 minus gamma, you transition to the safe state. Now, suppose my specification is a safety specification. It says, always make sure you don't reach the unsafe state. In other words, it is saying always make sure you reach the safe state. Then in this MDP, I hope it's clear that there is only one optimal policy, and that optimal policy is to take the action A from the initial state. Because if we took the action B with any probability, then there would be a non-zero chances of landing up in the unsafe state, which violates our specification. So in this case, there is only one optimal policy, and that is to take the action A from init. Now, if the transition properties were known, then we could have easily solved this problem, right? Because we can analyze the MDP, at least manually we can analyze the MDP and we can solve it. And turns out within probabilistic model checking, algorithms to solve these kinds of problems are well understood, right? And the core of these things is you want to ask, can we learn an optimal policy using just a finite number of samples? The idea is if you know the least non-zero transition probability, then from every state, you can sample every action roughly 1 by p min number of times. And if you do that, then roughly you know what the whole topology is. And as long as you realize that there is a transition from initial to unsafe, we don't need to know what the probability gamma is. As long as we know that there is a transition with whatever probability it may be, then with very high chances, we have a very good estimate of the transition probabilities. And once we have a good estimate of it, we can use probabilistic model checking. Right? So let me recap what we just did here. We asked that, can we find the optimal policy, assuming transition probabilities were known? And we say that even if we did not know the whole transition probabilities, we just knew the minimum non-zero transition probability. I can design a sampling-based algorithm that samples every action from every state, roughly 1 by p min number of times. And then when I do those many samples with very high probability, I will be able to find a good estimate of transition probabilities, and therefore I'll be able to use probabilistic model checking. However, Now let's analyze what happens if the transition properties were not known, right? So now we are going into the RL domain. Now here is what we are, right? It's the same MDP, it's the same specification. There is only one optimal policy, which is to take action A from init. And the question is again, how many samples should I take in order to ensure that I learn the optimal policy? Now, remember, we do not know what the transition properties are, so we do not know what P-min is. So here is the algorithm I propose. I say, well, suppose I sample k number of times. So from every state, I sample every action k number of times. Now, suppose my k were, in particular, suppose I sample the action B from the initial state k number of times. Then now suppose k was significantly smaller than 1 by gamma, right? We don't know what the number of, our whole objective is to find what this number k should be. Now suppose we've chosen a value of k and k ends up being significantly smaller than gamma. Remember, we don't know the transition probabilities, so we don't know what gamma is, right? So suppose we choose a k such that k is significantly smaller than gamma, then there are very high chances that we may never discover there is an edge from the initial state to the unsafe state. And if we don't discover that edge, we might as well conclude that, well, all samples from the initial state on action B have landed in the safe state. So it must be the case that taking action B from initial state is an optimal policy. So you see, simply by removing the assumption that we know transition probabilities, now assuming we don't know transition probabilities, no matter how many samples I take, how many samples k I take, I can always design an MDP where it will always produce the incorrect optimal policy. And this is even on this really simple 3-state MDP with a really simple safety objective. So we can take this insight, and indeed we are able to prove that in the case of reinforcement learning from temporal logic specifications, one cannot design a pack learning algorithm. So there does not exist any reinforcement learning algorithm that learns from temporal specifications where we can guarantee that you will learn a near optimal policy within a finite number of samples. Well, that is a very key negative result against RL from temporal specifications, that there cannot be a pack learning algorithm. So what can we do instead? Well, there is a lot of work in trying to build guarantees from learning from in reinforcement learning from specifications. And oftentimes the flavor of these results are along the lines of, suppose I take mild assumptions on the MDP. For example, if I assume that you know the least non-zero probability, we don't need to know all the transition probabilities, but suppose we know a lower bound on the least non-zero transition probability, then one can find a pack learning algorithm. And similarly, there are various other assumptions one can make under which pack becomes possible in the RL setup. The other line of work says that, well, perhaps I don't want to make assumptions on the MDP, but I can assume things on the length of trajectories that I can sample. So if I assume something about the length of trajectories I can sample, even then we have been able to show that one can obtain pack guarantees from learning algorithms. And another recent line of work that is being pursued is whether one can generate asymptotic guarantees from can obtain algorithms with asymptotic guarantees of convergence. And turns out in the case of reinforcement learning from temporal specifications, asymptotic guarantees are possible. Currently, this work is purely theoretical. We are looking at trying to build practical algorithms with asymptotic guarantees as well. So to summarize summarize the landscape of theoretical guarantees, in terms of theoretical guarantees, under rewards, both pack and asymptotic guarantees are possible. However, in temporal specifications, pack is possible only under mild assumptions on the MDP. If we do not make any assumptions on the MDP, pack guarantees are not possible. However, asymptotic guarantees of convergence are still very much possible. Well, so far so good. We have discussed RL, we have discussed rewards and temporal specifications with respect to ease of task specification and theoretical guarantees. Now let's shift gears to algorithmic performance. So without getting into too much detail, All I will mention is that when it comes to reinforcement learning from rewards, it is known that learning from rewards is extremely good for short horizon tasks. However, if we try to learn long horizon tasks, where we say do A, then do B, then do C, then do C, and so on, reinforcement learning algorithms from rewards actually suffer. So the question is, what happens to learning algorithms from temporal specifications? Now, the very 10,000 feet view of how these algorithms work is that we take a problem of reinforcement learning from temporal specifications, reduce it to a problem of reinforcement learning from rewards, and then we use one of the state-of-the-art algorithms of RL from rewards, such as Q-learning, PPO, DDPG, and so on. And whatever policy we obtain by optimizing from rewards, we use that as the policy for RL from temporal specifications. Now, as I said previously, RL from temporal specifications actually does not have any guarantees. However, RL from rewards has. So there must be a sort of a disconnect between these two. So it turns out that these translations are not preserving optimal policies. However, for most tasks, these work well in practice. So although this is the template, this is the algorithmic template that all algorithms that learn from temporal specifications employ, this template does not offer any guarantees, but it certainly demonstrates good performance in practice. However, there is a key issue, which is that because of this reduction to rewards, RL from temporal specifications ends up inheriting the issue of RL from rewards, which is that RL from rewards is myopic, and reinforcement learning from temporal specifications inherits this automatically. So there is myopia in RL, which is that it is good at short horizon tasks, but poor at long horizon tasks. Let me illustrate this through an example to make it a little bit more clear. So we are returning to the same 9 rooms environment. S0 is the initial state distribution. S1, S2, and S3 are 3 different regions in the 9 rooms environment, and O is an obstacle that must be avoided at all costs. Now, suppose we have a short horizon task, which is either visit S1 or visit S2 while avoiding O. Right? So our task is either visit S1 or visit S2 while avoiding O. So either of the 2 trajectories demonstrated by the orange dotted line, either of those trajectories satisfies the specification. Now in this graph, I have demonstrated the performance of several state-of-the-art algorithms that learn from temporal specifications. The x-axis shows the number of samples. The y-axis shows that what is the probability with which the policy learned after X number of samples satisfies the given specification. And the better graph is the higher it is, the closer to the y-axis, the better the performance of the learning algorithm. So here we see that when the task is short horizon, then most of these algorithms perform very, very well. They're able to converge within very, very few number of samples. They're able to converge to an optimal policy with very, very few samples. However, let's make this specification slightly little more complicated. So now suppose our specification is either visit S1 or visit S2 and then visit S3, all the while avoiding the obstacle. Then on this graph, this graph shows the performance of the state-of-the-art algorithms, and I really have not forgotten to plot the graph. This is the performance of the state-of-the-art algorithms. If you make the specification 1 bit longer, all of the algorithms fail to learn anything reasonably. Even after a few millions of samples, the best probability with which they have been able to learn a policy is close to negligible. So what's gone wrong? Now here is what has happened, and this is what myopia refers to. In the first case, when the objective was to learn to reach either S1 or S2 while avoiding the obstacle, then most of these algorithms end up learning a policy to visit S2. Now, the reason visiting S2 is the policy that most of these algorithms learn is because it is easier to learn to visit S2 through an obstacle-free path than it is to learn to reach S1 through a path that navigates around the obstacle. So in the short horizon, so now this is what most of these algorithms end up doing. They learn how to visit S2. Now, in the case of the longer specification, as you may have noticed, in this environment, visiting S2 is actually futile because there is no path from S2 to S3, and the only path is one that actually navigates through the obstacle. So what ends up happening here is that as reinforcement learning algorithms start to learn this policy, they learn how to visit S2 because in the short horizon, it is the easier task to fulfill between S1 and S2. The issue, however, is that in the long horizon, S2 ends up being a locally optimal choice from where there is no global way of satisfying the specification. So what these algorithms are lacking is a high-level perspective where the algorithms are informed that even though some choices may seem harder in the short horizon, in the long horizon, they may be the better tasks to fulfill. And that's exactly what we are able to incorporate. So we have developed an algorithm called DIRL, which combines this high-level knowledge that a specification can provide with low-level reinforcement learning to learn locally optimal policies. So the specification language we use here is called Spectral. It consists of specifications. Spectral consists of using Spectral, you can write tasks which are safety tasks or reachability tasks or their combinations. For example, eventually B says you must reach a target eventually. Always is a safety specification which says fulfill a task while always remaining safe, while always fulfilling the predicate B. You can concatenate, you can sequence such reach avoid tasks, and you can take their disjunctions. And this is usually, this language is sufficient for various tasks in control policies. Now what we have been able to show is that for each spectral specification, one can construct a specification-guided abstraction of the environment such that every edge in the abstraction is a subtask and every path from the initial to the final state of the abstraction satisfies the specification. So in this case, when we're looking at the specification of visit S1 or S2, then S3 while avoiding O, the abstraction is a four-state abstraction, four-state DAG as shown in the diagram. S0, S1, S2, S3 represent the corresponding regions in the environment. The edges between them, so the edge from the task from the state Si to Sj, demonstrate the task demonstrates the task of reaching Sj from Si, and the paths from S0 to S3. S3 is the final state here. S1 is the initial state. Every path from S0 to S3 satisfies the specification. So now this abstraction gives rise to a very simple compositional approach to learning a policy, where in the decomposition phase, we use the first property, which is that every edge is a subtask. So we can decompose this long horizon property into several simpler subtasks demonstrated by each edge. In this example, there are four subtasks, namely the subtask from going from S0 to S1, S0 to S2, S1 to S3, and S2 to S3, all the while never visiting the obstacle. And in the composition phase, we use the second property, which is that once we have found policies, once we have learned policies for every edge, can we just find the best policy from the initial state to the final state in the DAG? So at a very high level, in the decomposition phase, we learn a policy for every edge. So we learn a policy pi1, pi2, pi3, pi4 for every edge. Each edge is a really simple short horizon task. So we can use an off-the-shelf reinforcement learning algorithm or any of the existing algorithmic templates that learn from temporal specifications to learn each edge. And once we have learned each edge, now we want to find the best path from initial to final. The best path is effectively the best policy. And the idea of best here is that whichever path has the highest probability of satisfying specification. And the way to find the highest probability of satisfaction is that a priori, we only have policies for each edge. We can use these policies to estimate the success probability of each edge. And once we have the success probability of each edge, we simply want the path that goes from initial to final with the highest probability of satisfaction. So in this case, what we will note is that the probability of success of the edge from S2 to S3 is close to 0. So there's a policy pi4 which satisfies the task of visiting from S2 to S3 with negligible probability. Therefore, there is only one path which is able to solve the problem, and that is to go from S0 to S1 to S3, which is actually the policy we want to learn in this case. Now, there are a few more subtleties to how this works, and those are to do with how one learns a policy for every edge. In particular, this is a very technical thing that to learn a policy from every edge, one should be able to sample trajectories that begin in an intermediate state. So typically, reinforcement learning does not allow you to sample a trajectory that begins in an arbitrary state. For example, if we want to learn the policy from S1 to S3, RL will require it to be able to sample trajectories that begin in S1. So there is a way to get about it. I will not get into the details of how that happens, but this is just for you to know that there is a little bit more technical aspects to making sure this algorithm works in practice. Turns out that, and this has to do by inducing state distributions or intermediate states so that one can sample trajectories from intermediate states in the DAG. I will not get into the details of how that happens. All that we need to know for the purpose of this talk is that there is a way to sample trajectories, to learn policies for trajectories, and learn induced state distributions on intermediate states so that one can learn a policy, the best policy in the DAG, in a single pass of the DAG. So what that means is that in theory, the best policy can be learned in a single traversal of the DAG, not more, not less. And during this traversal, each edge is called exactly once using a reinforcement learning oracle. And so in theory, this algorithm is extremely efficient. Also, the size of the DAG is polynomial in the size of the specification. So the total complexity of this algorithm is very, very efficient in the size of the specification, in theory. This algorithm is also extremely efficient in practice. So the two parameters that we care about is how does this algorithm scale as the specifications become more and more complex. So to demonstrate that, I have this 16 rooms environment here. I'm going to use the shorthand box x to y to indicate the specification that says starting in a region X, we want to visit a region Y. And while doing that, we want to visit one of the corner points, C1, C2, generated by the rectangular triangle produced by X and Y. And all the while avoiding obstacles along the path. Of course, here the red dots indicate the obstacles. So for instance, I could have a specification that says box A to B. So that is the specification indicated by the dotted line on the graph, on the illustration, on the environment illustration. And we can see that for this specification, in this larger environment, most state-of-the-art tools do very well. The performance of DIRL is demonstrated by the dotted blue line. And you can see for this specification, DIRL has the best performance. As earlier, X is the number of samples, Y demonstrates the probability with which this policy learned after X number of samples satisfies the specification. So the higher the specification, the higher the graph, the closer it is to the Y-axis, the better the performance. And for this specification, box A to B, a lot of the tools do very well. DIRL does the best, which is our tool. But the key thing to note is that as we make the specification more and more complex, so now suppose the specification is first to box A to B and then to box B to C. Now the specification has become more complex, and as the specification becomes more complex, performance of other state-of-the-art tools starts degrading, whereas DIRL remains, the performance of DIRL still remains very, very consistent. And we keep seeing this trend even as we make the specification much longer. And we can keep extending the specification here, and we keep seeing that as the specification becomes longer and more complex, in this case, it has both disjunctions and many, many sequencing. DIRL is the only tool which is able to scale with the length of the specification. The other parameter for practical performance is of how do these algorithms scale in the dimensionality of the environment. So here is the simulation of the Baxter robotic arm. This is open source available through OpenAI Gym. which is a standard reinforcement learning library with lots of benchmarks and lots of environments. And we see that on environments like this, which are extremely high dimensional, DIRL is perhaps the only tool that is able to learn anything of substance within a reasonable number of samples. So DIRL has good performance across both parameters of scalability, both in terms of complexity of specification and complexity of environment. The other thing I want to touch upon is beyond just scalability in terms of specification complexity. One thing that reinforcement learning suffers from is the lack of generalization. So oftentimes when we think about training a reinforcement learning policy, we think about training one policy for one specific task. Now, this is actually a limitation of existing reinforcement learning approaches because when we think about reinforcement learning, oftentimes the intuition comes that we're trying to imitate human learning. So if you give enough feedback, if you sample enough number of times, one is able to gather a sufficient intelligence to not only solve the problem given, but also solve simple related tasks. So for example, here, I'm demonstrating this in the diagram on the left. I've demonstrated a class of problems which are very similar to one another. So these are all reachability problems which say from R0, visit the gray dot given above, or from R1, visit the gray dot, or R2, or R3, R4, and R5, and so on. So not all of these are reachability tasks, and even as reachability tasks, these tasks are very similar to one another, right? So intuitively, we would expect that suppose I ask a reinforcement learning algorithm to train on not all of these tasks, not all of R0 to R5, but suppose you only train on the first two tasks, R0 and R1. Is reinforcement learning able to learn policies that can generalize then to solving the tasks R2 to R5? Of course, note that these are the simplest kinds of specifications you can have from temporal specifications. It's a simple reachability task. In each of the tasks, they differ only in the position of the initial state, nothing else. The goal is the same, only the initial states shift to the right slightly. And on the plots shown on the right, I have shown the performance of reinforcement learning algorithms. And what I'm showing by the lines in blue are the trajectories produced by these learning algorithms. So you can see that for all of these algorithms, and some of these are actually state-of-the-art reinforcement learning algorithms that are designed to have generalization, we can see that very few of these trajectories are able to visit the goal region in pink. So although these tasks are very, very similar, if you train a reinforcement learning algorithm, the policies do not generalize even to the simplest shift in initial states. So this is another issue with reinforcement learning, which is that existing algorithms completely lack generalization abilities. And this is even true for an algorithm like MAML, which is a meta-learning approach that is designed to perform generalizability. What we have been able to show is that when you use temporal logic specifications, one can actually design reinforcement learning algorithms that generalize well. I will not get into the details here, but the key idea is that as long as specifications have structural similarities and they differ only in the grounding of the predicates, for example, in the reachability example I showed, the task is the same. The task is to reach a fixed goal. The only grounding predicate that changes is in the instantiation of the initial states. And then we are able to design generalization reinforcement learning algorithms that leverage the similarities between tasks and are able to generalize to unseen tasks, even upon training on only a few of them. Another example is this tower destacking problem. Suppose you want to destack a tower of blocks, and the idea of generalization here is that by only training on the top two blocks, can you destack the entire tower? And once again, here the tasks of destacking each block are related to one another. The only difference is that when you destack a block, the only difference lies in the initial position of the block and the final position of the block. As the tower is destacked, the initial position keeps coming down and the target position keeps going up. Otherwise, there is no difference in what the tasks are. Temporal logics are able to capture these inductive similarities, and we are able to design algorithms that can leverage inductive similarities to generalize across other similar tasks. And this is work that my PhD student has been pursuing currently, and we're working on improving the scalability and verifiability of these algorithms. So, talking about algorithmic performance, learning from rewards is good in the short horizon, but they're very poor in the long horizon, primarily because they suffer from myopia. Temporal logic specifications can combat that. They can learn very long horizon tasks in complex domains, while also facilitating generalization, which is a feature that most learning algorithms suffer from. So, this is the summary of the table of what we know about theoretical guarantees and algorithmic performance of learning from rewards versus learning from temporal specifications. But if you look closely at this picture, we see that what is theoretically possible is not practical, and what is practically possible does not have theoretical guarantees. So in the progress made in learning from temporal specifications, there is a gap between the theory and the practice. Theory is not practical, practice is not theoretical guarantees. So the next question is, how do we merge the two? And there are two ways that we have been thinking about addressing this problem of achieving both practical performance and guarantees from learning algorithms. And the stem and the germ of this is that reinforcement learning algorithms can give you asymptotic guarantees of convergence. So the question we ask is that, well, until now we were asking algorithms to give guarantees from algorithms to have synthesis-like guarantees. So you want to design an algorithm that has guarantees of correctness, that produces an output with certain guarantees, either back or asymptotic guarantees. But now we'll take the other view. We'll take the verification view, which says that if I give you an environment and I give you a specification, can you tell me whether, and if I give you a system, can you tell me whether the system satisfies the specification? Now, this is based off a recent article that appeared in CSEM last year, which talks about, in addition to simply saying yes or no, what we also want for AI systems is a certificate of correctness. And the reason we want a certificate of correctness is because AI systems are often deployed to non-experts. And if a non-expert wants to gain trust in the AI system that they are working with, they will hardly be able to use a verification algorithm. Instead, if we give them a proof of correctness that they can verify independently without having to analyze the whole AI system, that would be significantly better for domains where auditing of systems is required. So the verification of AI systems should be accompanied with a certificate of correctness. In the case of reinforcement learning, if the environment is known, so if we have an MDP where the transition properties are known, there is a rich literature on certification of temporal properties. On the other hand, there is starting to be a lot of work on designing certificates in unknown models, in reinforcement learning models, but these certificates don't have guarantees. So even if I give you a certificate in the RL domain right now, there is no way of ensuring that correctness of the certificate implies correctness of the system. So in a line of work that we are pursuing right now, we are looking at whether we can develop a theory, whether we can develop the foundations and tools of certification with guarantees in the RL domain. So until now, I spoke about the synthesis problem. We want to learn with guarantees. Now we're talking about the verification problem, which is that if you give me an RL policy, it may or may not be generated from an algorithm that gives guarantees. It could be generated from any source. If you give me an RL policy and you give me a specification, I can verify its correctness. And in addition to the correctness, I can also produce a certificate that can be checked by a third party. And we want to do this with guarantees. And we are starting to have initial works where we can show that in theory, it is possible to learn certificates with guarantees. And now the work is whether we can make these tools practical. So there is both the synthesis view of AI systems and also the verification view, which says learn a certificate with guarantees as well. And the other direction goes back to the synthesis problem. So until now, we were talking about guarantees from back, and turns out learning from temporal logics does not have guarantees from back. However, we do know that it is possible to develop algorithms with asymptotic guarantees. The issue right now is that these algorithms are very, very theoretical. They're purely theoretical. They are what are called model-based, which means that we will not be able to apply them for continuous state environments. They are limited to MDPs with finite states. MDPs in the real world are not finite state environments. They are continuous state, continuous action environments. So the question becomes, can we design reinforcement learning algorithms with asymptotic guarantees that can be deployed on continuous states and continuous environments for real world applicability? And the way we are approaching this is that we want to design model-free algorithms, which can also be integrated with neural architectures so that they can be deployed in real systems. So these are the two directions of research in terms of obtaining further trust from reinforcement learning from temporal specifications. So to summarize, so the much broader view here is that our objective is to obtain trustworthiness in AI systems, and we take a formal methods approach. Typically, we talk about functional correctness. We want to know whether the output is satisfying a given specification, or whether we can produce an AI system that satisfies a given specification. But beyond functional correctness, the scope of formal methods in AI is immense. For instance, we discussed the problem of generalization. Generalization is very hard when you're learning from rewards, but if you introduce temporal specifications, we can already start leveraging that in order to obtain better generalization. And we are looking at trying to see whether we can also ensure that these algorithms have guarantees or not. There are other avenues where formal methods could be deployed in the space of interpretability and explainability, and of course, the critical question of safety for safety-critical systems. To summarize the talk so far, to summarize today's talk, we were looking at specification-guided reinforcement learning, and the central theme being, can we use formal methods to build trustworthy AI systems or not? We compared how reinforcement learning is operated under rewards, which is the traditional way of reinforcement learning, versus reinforcement learning from temporal specifications, and we see a broad comparison between the two approaches. And I will leave it to your judgment to decide whether formal methods is building further trust in AI systems. Thank you for your attention, and I'll open the floor for questions now. Thank you.
All right. Well, thank you so much, Suguman. Excellent talk. I have a bunch of questions, but let's see what we have from the audience. Go ahead, Olga.
Yes, hello. Sorry, my PC froze for a second. I hope I did not miss anything. Okay, we're starting with questions, right?
Yeah.
Okay, let me see. Is there a research paper on this?
Yes. So I did pepper the talk with several research papers. So we had presented a tutorial on this at AAAI. This is a AAAI 23 tutorial. If you go at this link, you should be able to find it, where a lot of these research papers are available. Another good source for research paper references is our CSAM article, which appeared in the February edition this year. So literally 20 days earlier, that's when the paper came out. It's called Specification-Guided Reinforcement Learning, conveniently. That paper also has references to a lot of our results and results from the community. So that would be a good, a single point reference would be the CSAM article.
And we'll send out the slides that will have these pointers. So.
Yeah.
Yeah, thank you. Okay, the next question. What is the equivalent states S1, S2, S3, S4 in the Baxter environment that you similarly mentioned for the 3x3 or 4x4 grid environment?
Yeah, so that's a pretty good question. Let me just pull it here. So in the Baxter environment, so these abstractions are specification-guided abstractions. So for these cases, the specification here was to pick up a block from its current location and to move it to a different location. So in this case, the abstract states represented the configurations of the Baxter robotic arm and the position of the block, depending on where it was. So if initially the block is located here and the robotic arm is here, or depending on wherever the robotic arm is, the set of all of those things is the initial state. And the final state there is where the block has been shifted to the target state and the robotic arm is perhaps holding it right there. So that could be another state, and so on and so forth. So here, effectively, abstract states are a set of configurations of the environment. And in this case, it would be the position of the robotic arm and the location of the block. So, and of course, this is with respect to the dimensions of the robotic arm. So these are not visual inputs. In this case, these are the 7 degrees of freedom and so on.
Thank you. At the moment, we are done with questions from YouTube. Now moving to questions from Discord channel. How do you specify those temporal specifications other than by hand? Can this framework also be used for that?
Could you repeat the question? I'm not sure I followed it.
Yeah. How do you specify those temporal specifications other than by hand? Maybe it was related to a particular slide.
Yeah. So that's a very good thing you've noted, that right now, all of the tasks we are looking at, we are assuming we can specify its temporal logic specification by hand, right? And this is usually how formal methods. This is an assumption formal methods makes, that whenever we're using temporal logic as a way to specify tasks, these specifications are expressed by hand. In our case, when we're looking at the RL domain, also the predicates, the grounding of the predicates, we are assuming it is done, at least not all of our experiments, we are grounding by hand. However, your question does allude to a very key criticism of manual expression of temporal logics, which is that sometimes even designing temporal logic specifications can become very challenging, especially grounding of the predicates in our case can be very hard. So there is starting to be a lot of work which also says that if I just give you some demonstrations of what good trajectories should look like and what bad trajectories should look like, can we learn the temporal logic specification? So you can think of this as inverse reinforcement learning, which is that through demonstrations, you want to learn the reward function. There is starting to be a lot of work, which is sort of inverse reinforcement learning for temporal specifications, which is if I give you demonstrations, can you automatically generate the temporal logic? And can you automatically do the grounding of predicates? That is also a research direction and an important one.
Mm-hmm. And a follow-up question from me, related one. So you mentioned this DAG that you use in your approach. So this is created manually, right? You do not create this automatically.
So once the specification is given, the DAG can be constructed automatically. But the specification needs to be given manually. Once there's a specification, the DAG is generated algorithmically. We do not do any manual. There is no manual effort once a specification is given.
Mm-hmm. Mm-hmm. Okay, thank you. For researchers interested in pursuing the generalization path, where would you suggest to start? Any chances of collaborations?
I would love opportunities for collaboration. So we have recently published, this is work that my PhD student is pursuing. We recently published a paper on this at ATWA, which is a formal methods venue last year. It's called Inductive Generalization in Reinforcement Learning from Temporal Specifications. I'll be happy to share that paper if there's a way I can do that through Centaur. But I would say this would be the starting point, and I'm very excited about this direction. I think temporal logics offer what, in the case of generalization, temporal logics can offer exactly what rewards fail, which is that even if two tasks are very similar, their rewards will look very different. But if two tasks are similar, the temporal logic will scream that they are similar tasks, and they differ perhaps only in the grounding of the predicates. So this is an insight that I really think that can be, one can run with this insight to obtain generalization. So I'm very interested in this direction of research. Please reach out to me I would love to discuss this further. And we're actively working on this. So I'm this is very topical for my research interests right now.
Great. So maybe, Suguman, you can leave your contact for interested people to be able to reach out.
Yes, I will. So it is
Okay.
my first name at gatech.edu. So SUGUMAN at gatech.edu.
Okay. Thank you. Okay, the next question. What are your thoughts on targeting continuous environments where determining abstract states is difficult to do so?
That is true. So in our case, a lot of that difficulty gets masked by writing the temporal logic specification. So for instance, in the Baxter robotic arm, as I said, the predicates, the abstract states, which is actually, if you think about it, perhaps I can go to this example here. Maybe this example will demonstrate it well. Or maybe one slide earlier. Yeah, this slide here. So if you look at this slide, then the specification says S1, S2, S3, and O. And S1, S2, S3, and O are actually regions in the environment. So these are the predicates, right? So S1 refers to the predicate that a state is within the region S1. S2, S3 similarly. And O also refers to the predicate that a region is in the, a state is in the region O. So in our case, a lot of the effort of writing of finding the abstract states actually gets masked by writing the specification. So this is certainly what I was saying. There is starting to be a lot of research on how do you do automatic predicate grounding as opposed to doing it manually. I hope that answers your question. For our purpose, as long as the specification has all of these things done carefully, we can get it. We don't concern ourselves with correct grounding of predicates and so on.
Thank you. The next question is, what about the argument that with the temporal specifications, you get to big O of n cube complexity for temporal constraints versus using more samples of lower compute complexity for RL training?
So I would argue this is not a challenge at all. So when we are given spectral specifications, I do not get into this too much in detail, but perhaps this is the opportunity to do it. So when you're using a spectral specification, what we've been able to show is that the size of the DAG is linear in the size of the specification, and the number of edges is quadratic in the size of the specification, right? And now, if you think of how many reinforcement learning calls is this, because we need to learn each edge at most once. We learn each edge at most once. So you can think of it as a quadratic number of reinforcement learning calls. But notice that these are reinforcement learning calls to simple tasks. Each task is either a simple reachability task or a simple reach avoid task. This is not a complex specification. So we have traded off number of reinforcement learning calls versus the sophistication of what the reinforcement learning is supposed to do. Compared to how this would have worked if I were trying to learn the more complex specification, if I was trying to learn reach S1 or S2 and then get to S3, as I showed you in the plot, as I showed you in this plot, even state-of-the-art algorithms are unable to solve them. And this is after millions of samples. So anything we can do to improve that scalability is a critical contribution. So I wouldn't even think of this as a trade-off. I actually think this is necessary to be able to scale to long horizon tasks. And the good thing is that we can do it entirely automatically. Once you have a specification, the sub tasks are easily identified. Once the subtasks are easily identified, the algorithm is a single pass, at most a single pass over the DAG. So it's not even that the DAG has to be, every single edge will be learned. So in terms of theoretical efficiency, this is a very efficient algorithm. And in terms of practical concerns, there are many number of reinforcement learning calls, but each reinforcement learning call is for a very simple task. And if you compare it to what an RL algorithm would have been able to achieve if we hadn't done the decomposition, the answer is right in front of you. It would have learned nothing after million of samples. So this is I would argue this is a reasonable trade-off.
Thank you. The next question is, are there other commonly used specification logics being used in addition to the temporal logic you've described?
Yes. So even within the realm of temporal specifications, so we have been working with spectrum, but there are algorithms that learn from linear temporal logics, signal temporal logic also, because signal temporal logic is able to talk about continuous time. So signal temporal logic is also being used extensively for reinforcement learning algorithms. LTL over finite traces, which argues that LTL, linear temporal logic, is all infinite sequences, but really in RL, all you require are finite traces. So there's something called LTLF. So these are just a few, but there are many other temporal logics that are being used. Beyond temporal logic, so temporal logics are mostly used when you're looking at applications where there are long horizon trajectories, right? So they're executions. But perhaps one can imagine tasks that are just encoded in the form of a Boolean formula, right, or an SMT formula. And perhaps that would be another avenue of research, if it makes sense to express a task like that. But normally when one thinks of reinforcement learning, you automatically think about trajectories, right? So yeah, so I'm not sure if there's work on RL from Boolean logic specifications or RL from SMT specifications. Perhaps one should look into it.
Thank you. The next question is, there is a related work on using temporal specifications to refine specifications based on the counterexamples outputs of model checkers. A learning algorithm then helps correcting the initial model specification. Any relevance of that work with respect to your work? And there is also a link provided, but maybe if you don't think you can answer right now, maybe later you can look at the link and answer on Discord, or if you think you can answer at the moment.
Yeah, so I'll thank you for the reference. I'll certainly look into it. If I understand your question, or if I understand the theme of your question, what you're alluding to is perhaps specification refinement, right? And I think it is very relevant even to the problem that we are looking at. Because suppose in this case, right now, the specification I've designed is visit S1 or S2 and then S3, right? But what if I had a specification that simply said visit S3? Right, and now as we have seen through this example, that if the specification was simply visit S3, perhaps RL would have run into the same myopia issue, and we would have seen a graph as shown on the right-hand side, which is zero performance even after many million of samples. So what I'm alluding at is, right now, in all of our examples, if you really think about it, the specification is already giving the deconstruction of the subtasks. But if one were to specify, but the natural specification may not have necessarily involved having S1 and S2 as intermediate goals in the specification. A natural specification would simply have been go from S0 to S3. So in these cases, I think it is important to ask, in case a specification is unsatisfiable even after learning, is it unsatisfiable because the task cannot be satisfied in the environment? Or is it unsatisfiable because the specification is very coarse? So in this case, if I said from S0 to S3, it would have been unsatisfiable, or it would have seemed to be unsatisfiable because the specification is very coarse. Perhaps it would have helped if we could have learned that if you can insert a waypoint in between, like S1, then it would be able to decompose into simpler tasks and then be able to learn the specification. So if you are alluding to the question of specification refinement, I think there is scope for doing that in the RL space, and certainly in the RL for specification space.
So since we only have a few minutes, maybe I'll throw in some comments here in the remaining time. So, and anybody we missed, sorry, well, maybe Suguman can jump on Discord if she has time and
Absolutely.
address any other questions.
Yeah.
But I think this discussion we're having now kind of is really important. First of all, I love your. I think you have some really important results. This compositionality, I do believe, is extremely important for out of distribution generalization. It's,
Thank you.
I would even say it's the only way. But I think here, when it's clear that you must have the decomposition. I mean, the decomposition is key to the efficiency, right? So, but if you look at some of these, at least when I see things like do A and then do B, that's, or go to this state and then go to that state. That's sort of imperative or in nature rather than declarative. That's like, you could say, or it's like, it sort of gets into a planning, it reminds me of planning, right? So in effect, you're partly giving it a plan
Yes.
as opposed to letting it discover the plan.
Yes.
So, which would mean, as opposed to saying, do go to this state, then go to that state. A different, more indirect way, I think more declarative way would be to say, you can't visit this state until you have visited that state. And that's the kind of thing that you effectively express with preconditions and postconditions in planning. So my general question is that there's some relationship with planning here, and the way which is another, of course, strain of logical,
Yes.
specification in effect for, some kind of sequential decision making. So what has planning, AI planning, been sort of related to this LTL style, spec?
Yes, absolutely. So planning has been a motivation to a lot of this work. In fact, in very broad strokes, planning folks discover temporal logic as a way of figuring out that, it automatically gives you the decompositions and so on and so forth. But the key difference between planning and RL is that planning usually assumes that you have a map of the environment, so the environment is known. So in terms of the terminologies I use through this talk, I would say planning is actually the probabilistic model checking problem. Whereas RL is saying that you do not know the environment. You know nothing about the environment. Now can you do it? And in fact, a lot of the early work in specification-guided RL is from people who had been working on planning. So on this slide, some of the competing baselines are these RM baselines, like QRM, HRM, and so on. So this is a technique called reward machines, which has actually been developed by folks who are doing planning, and they realized that one could lift that work into the reinforcement learning space. So there is a very, very close connection between planning and this. And you're right, planning has a very imperative nature to it in terms of how one specifies the task. The more declarative we can become, the better.
But this sort of looks like you're, when you say do this, then that, visit this state, then visit that state, that's sort of, it's sort of like you're telling it how to solve it, as opposed to you're just telling it, properties of the dome of what you want, right? Specification sounds like I'm just saying what I want, but when I say do this, then do that, that's sort of getting into how
Yes.
to what I want.
Yes. So when I say it should be declarative, this is also related to what I responded to the previous question, is that in this case, the most declarative specification would have been reach S3. Right? And then you want the learning algorithm to discover that maybe there are intermediate points which are easier to reach. And then using those intermediate points and then do the decomposition and so forth. So this question of specification refinement, and perhaps one way to think of it would be that how do you go from a declarative specification to imperative one, which can be realizable. So a realizable declarative specification refined to a realizable imperative specification, also learned. So again, purely model free, you don't know what the environment is. Can you learn how to go from a declarative specification to an imperative one. I think that is an important sub problem if one were to try to make these techniques practical.
So, but I'm struck by, I mean, the theoretical result is really amazing. I think it looks like the, practical benefit is really large. So it looks very impressive. So why are you saying it's not practical, or what's stopping it from being sort of the ultimate tool in your view?
So this is so PAC is not possible. Asymptotic guarantees. This is very very recent work where we are seeing that it is possible to design algorithms with asymptotic guarantees, but the algorithm we have is very model based right now. To give you a to give you an intuition of how these algorithms work, asymptotic convergence, asymptotic guarantees lets you sample indefinitely. So in case you can sample an MDP indefinitely, then you would have learned the best possible transition probabilities, right? You would have learned the real transition probabilities. And if you've learned the real transition probabilities, it becomes a planning problem. It's no longer a learning problem, right? So that is why asymptotic guarantees is possible. But this idea that you have to sample an infinite number of times. So the way these algorithms work right now, it's purely model free. So we are explicitly learning the transition probabilities. In practice, you cannot do that. So this style of algorithms where you explicitly learn transition probabilities are called model-based algorithms. To make things plausible in practice, one needs a model-free algorithm, which learns the policies without explicitly learning transition probabilities. So I had started with this very high 10,000 feet view of how RL algorithms work, which is simulate to estimate transition probabilities and then use Bellman equations to obtain optimal policy. This is not how practical algorithms work. This is good for just getting a sense of how these algorithms work. In practice, if you have to estimate transition probabilities, your algorithm is not going to work. Think about this, right? If you have n number of states and a number of actions, from every state on every action, you can go to n different states. So the total number of transitions then square a, which is already very large. There is no way you can store that much information just to get one policy. So what asymptotic algorithms are able to do in the case of learning from rewards, and this is what Q-learning does, is that it is able to get the optimal policy without ever learning the transition properties explicitly. And that is what we need to do if we want to make RL from temporal logics a practical reality. And that's exactly what I meant by we want to learn direct model-free practical algorithms with guarantees. And in the case of Q-learning, the model freeness, the Q-learning approach has lent itself to neural architectures, which has meant that we have been able to design algorithms from visual inputs and whatnot. That is the direction we will also have to take if we want to make specification-guided RL a reality.
All right, so there you have it. Sounds like a great set of collaboration possibilities.
I would love to. Yes, absolutely.
Thank you so much, Suguman. And we'll provide on Discord ways to find her and
Yes.
learn about her work. And if you have time, you can jump on Discord, Suguman.
I would love to. If you can tell me how to connect to Discord, I will do that.
We will, definitely.
Absolutely.
All right. Well, thanks, everyone. And check out Suguman's work, and we'll see you next time.
Thank you. Thank you very much for the invitation. Thank you for your engagement. And I would love to engage in further discussions. Thank you.
All right. Take it, everyone.